In another video about electronegativity, we've talked about what makes a bond polar. But this video is about what makes a molecule polar. And what makes a molecule polar will depend upon the shape of the molecule. If you just look at a single bond, like the phosphorus-chlorine bond, you will find that the chlorine side is a little bit electronegative, and the phosphorus side is a little bit electropositive. We use these little deltas, delta plus, delta minus, to indicate which side is which. Sometimes we also use a arrow that points toward the more electronegative side, and we can also give it values of electronegativity. Phosphorus is 2.1, chlorine is 3.0, so the difference in electronegativity is 0.9, which we have said is a polar bond. So our question for this video is, does it make polar molecules? So to answer this, let's look at a couple of examples of molecules that contain the phosphorus-chlorine bond. The first one is PCl5. In order to determine the shape of that, we first draw the Lewis structure. So we have a phosphorus, and we end up with 5 chlorines around it, all of which have an octet. And then the phosphorus has more than an octet, which is okay for that element. So this is the Lewis structure. And that is not a shape, but that gives rise to a shape, and it is trigonal bipyramid. We're going to draw it with this triangle as a way to show that 3 of them are in a plane, and one is up and one is down. Okay, so that's the shape. Now, the bond polarities of the phosphorus-chlorine bonds going up and down will cancel each other, and the 3 in the plane will cancel each other. So all the polar bonds in this molecule will cancel, which yields a nonpolar molecule. So the answer to this question, does it always make polar molecules if you have a polar bond? The answer is clearly no. But let's look at another example, PCl3, when we draw that Lewis structure. We end up with an octet around every atom, and that again is not the shape, but we can tell from the Lewis structure what the shape is, and it ends up being trigonal pyramidal. In that case, the PCl bonds do not cancel because all of the ones that are there have this are in the general direction of down, as the way I've drawn it. There's no chlorine above to cancel those bonds. So in this case, the polar bonds do not cancel. Which yields a polar molecule. So again, it's important to understand that whether the bonds, when the bonds are polar, it does not necessarily mean that the molecule is polar. You have to look at whether they cancel. So let's look at these 3 examples below. I will do the first one for you, and then you should stop the video and try the other 2 yourself. So the process for determining if it's polar, first you need the Lewis structure. And then from that, you need to identify the shape. Okay, this has 4 electron groups. 2 of them are bonds, which means it has a bent molecular shape. And I can draw in the dots or not. And a bent shape cannot have the polar bonds cancel because they both, they're not equal and opposite. They would have to be opposite each other in order to cancel. So this is a polar molecule. Go ahead and try the other 2 molecules before going on and seeing how it's done, checking your work. Okay, so hopefully you've done these, but SO2, you will find there is a Lewis structure that looks like this. And incidentally, it will have resonance forms where the double bond is on the other side and the single bond is on the other side. And since there are 3 electron groups, 2 of them are bonds, you will find that it is a bent shape. Also, and bent shapes cannot have the bonds cancel. They're not across from each other, so it will be polar. The final molecule, krypton, with 2 iodines on it, you'll find that you have an expanded octet on the krypton, and the shape, the electron geometry is trigonal bipyramid with 3 lone pairs on the planar positions, which yields a shape that is linear. And a linear shape, if they are bonds to the same atom, both I's, then the bond of polarities will cancel, and this will be nonpolar as a molecule. So if you think about it, certain shapes, such as bent, can never be nonpolar. The polarities of the bonds can never cancel, so they will always be polar. And so I've written the list of the ones that will always be polar because the bonds can't cancel. All right, and so examples that we just did, OF2 and SO2, those are both bent, so they will always be polar. Trigonal pyramid, we did the example of PCl3, that will always be polar. The seesaw shape is another one. An example is SF4, and I'll draw that with wedges to mean that they are coming out at you. So on that one, the 2 F's across from each other are almost 180 degrees apart, so they will almost cancel, but these 2 going down will have nothing on the other side to cancel them. A T-shape will also be polar. Here's an example, BRF3. I'm showing the dots on the central atom sometimes and not always the side atoms for the shape. And then square pyramid will also be polar. And so I'm going to show BRF5. These 4 are in a plane, and then there's one more going down in this example. For all the rest of the shapes, other than these ones I gave you that are polar, whether it's polar or not will depend upon various things, including whether the atoms are identical that are in the bonds. So for all the others, polarity depends on whether the bonds are 2 identical atoms. So the example I'm going to give is 2 linear molecules that are very similar. Okay, and one is one we just talked about, krypton iodide, sorry. So that one we said the angles are 180 degrees, so those 2 bonds will completely cancel. But what if I replace one of those I's with something else, like say a chlorine? Then the KRI bond is not going to be exactly canceled by the KRCl bond, so that will be polar. All right, so let's just get some blank paper and practice a couple more. I'm going to suggest that you determine whether BCl3 is polar and whether CH2Cl2 is polar. So please stop the video and try to do that. You need to determine the Lewis structure, then the shape, and then see if the groups cancel, the bond groups cancel. For BCl3, you'll find that the Lewis structure looks like this, and you hopefully recall that boron is an atom that can take less than an octet. So you will not get an octet around the boron. And so there's only 3 bonds to the boron, which means it's trigonal planar. So its shape will look like this. Okay, so this is the Lewis structure. And this is the shape. And then you look at the bonds, and those 3 chlorines pull in such a way on this boron that they will cancel each other. So this is nonpolar, because they're identical bonds in 3 directions. All right, CH2Cl2 will have this for a Lewis structure. Okay, but again, that is not a shape. If you mistakenly think of Lewis structures as a shape, you would say, well, the H's are across from each other, the Cl's are across from each other, they'll cancel. That is not what happens, because the actual shape isn't what the Lewis structure looks like. The shape is tetrahedral, and you can make either a chlorine or a carbon going in the upward direction. It doesn't matter, because all the angles are identical. All right, so I have drawn it like this. You might also draw it with wedges to show the shape, to make it more clear. And it doesn't matter, again, which atom gets put in which position, because they are actually all identical, which you can see more easily with a model. All right, so they can't cancel each other. The chlorines aren't across from each other. Hydrogens are not across from each other. So this will be a polar molecule.